Hello and welcome to our potential energy diagrams and collision theory. Here we're looking at these are sort of showing almost like in diatomic form, and B molecules colliding. They're the reactants. They have 75 kilojoules of potential energy. And then something comes along, be it a flame, be it a lightning bolt. It could be energy from another reaction that happened nearby. But some kind of energy comes in and boosts the system. And it forms this activated complex where it's like a mega molecule. It's an intermediate molecule, highly unstable. And for just a brief moment, it forms, let's say this A2B2. And then it will immediately break apart. And it's basically the breaking of the bonds and the reforming of the new bonds. And so in terms of a forward reaction, we would kind of start here as reactants, go through this intermediary, and then form our products. And maybe we could call the products 50 kilojoules of energy for the potential energy of the products. So some things that we can ask about this, is this reaction endothermic or exothermic? And in order to do that, we can sort of draw a line across from where the product started at 75 and where they finished, let's say, at 50. And so in kind of doing that, we're making a calculation for the delta H, or the change in the heat, saying, this system started at 75 and it finished at 50. And in order to calculate for delta H, we're going to take the heat of the products minus the heat of the reactants. So the heat of the products in this case is 50 kilojoules minus the heat of the reactants, or the potential energy of the reactants. And so for a total a change in heat would be negative 25 kilojoules for that forward reaction. When we get a negative 25 kilojoules, this means that heat has actually left the system, it has gone out into the environment, and so we would consider this an exothermic reaction, because overall the system has lost heat. I like to think about it as like I went out with $75 in my pocket. I had a pretty good night, but I came back with 50. Obviously, I'm down 25. I have, released those $25 into the environment. And so when the heat is flowing out, or, it might feel hot to the system, heat is sort of being created as a product, that would be a characteristic of exothermic reactions. In terms of activation energy, we can see that we start at 75. We need to get up to 125. So here, we can do 125 is sort of required minus the 75 that we already are at. So 50 kilojoules needed. So that's the activation energy. And then that's the activation energy for the forward reaction. So these reactions, it can occur in one direction, and then possibly you can even go in reverse. So we would have our forward reaction, which is basically left to right, like we've always been reading them. But imagine, if you will, the 2AB suddenly reversing and becoming that activated complex again, that intermediate particle, and then decomposing into A2B2. So in terms of the reverse reaction, if we wanted to sort of take a look at that, let's look first at the activation energy. So in terms of my labeling, I might even want to put an F there for the activation energy of the forward reaction, whereas this is the activation energy of the reverse reaction. It's actually going to take quite a bit, right? So it's 125 that's required, but we're only starting at 50, so we're going to need 75 needed. And I wrote that in the wrong spot. So in terms of activation energy, 75 kilojoules are needed for the activation energy. In terms of the delta H, let's take a look here. And we're going to compare where we started. But again, we're looking from right to left. So the comparison then is here. So we're looking for the delta H of the reverse, whereas this guy here was the delta H of the forward reaction. So, but in terms of the reverse, we're going to have to, call these our reactants and these are now our products. So we'll do the same kind of calculation, but using those actual values. So the AB are now our reactants. The A2B2s are products. So we'll do 75 minus 50, which means 25 kilojoules plus 25 kilojoules in terms of the delta H. So the reverse reaction is going to be an endothermic reaction where energy is going to have to flow into the system from the surroundings. And in terms of the whole piece, find the activated complex. We can see that up top here. So let's take a look at another reaction. Or another potential energy diagram. And so in terms of, just looking at it in general, if you're asked endothermic or exothermic, they're generally asking about that forward reaction. They'll specify whether they want you to look in reverse or not, but generally it's always left to right. So let's take a look here. So in terms of the delta H, the change itself is a positive delta H. Heat has to come into the system. In terms of the calculation, we're going to do the product minus the reactant. So 40 minus 20 gives us a plus 20 kilojoules for the delta H. And that is representative of an endothermic reaction. The activation energy required for the forward reaction, don't get caught up with these dotted lines. Go back to your reactants, and this forms your activation energy of the forward reaction. So let's take a look. So 70 minus 20. So 70 to the top and 20 to where the products, potential energy of the products are. So In terms of the forward reaction, the potential energy of the reactants are at 20 kilojoules, and the products themselves are at 40 kilojoules. If we look in reverse, we can see an activation energy here. So this is now our reactants, a slightly lower hump to get over. So we would compare 70 minus 40. So 30 kilojoules are required for the reverse reaction. And the overall delta H for the reverse reaction is in here. And it'll be a negative delta H for the reverse reaction. Again, we want to use products minus reactants. This is for the reverse reaction. So we're seeing a negative 20 kilojoules. And you absolutely really have to have that negative there. Super important.